Hello everybody, welcome to today's lecture. Today we're going to be talking about the structure of the atom, starting out on chapter 16, section 1. The first thing that we're going to talk about is the atomic particles themselves. Remember that elements are made up of only one type of atom, and that particular atom is what gives the element its properties. So if we're talking about iron, for instance, only type of atoms that are in iron are the iron atoms, and they're very specific, and we're going to learn about those. I'm going to talk also about what makes up an atom, which is why this slide is titled with the subatomic. Just know that atoms are divided into different particles. The first thing we're going to talk about is the nucleus. The nucleus of the atom is the small positively charged center of the atom. All right, and inside the nucleus we have protons, and a proton is a particle that has a positive 1+ charge. So some atoms have multiple protons, and we'll talk about the difference there. The other type of subatomic particle that is in the nucleus is the neutron, and this is a particle that has no charge, and we have the tilde 0 charge. So they are made up of no static charge at all. And on the outside, we have electrons. These are the particles that surround the nucleus in a cloud. Some of the atomic models that we use show these nice little circular hoops where electrons zing around. And now we know that it's not exactly accurate or true. They actually surround the nucleus in a cloud type pattern. They're just kind of everywhere. And they make up most of the size of the atoms. Most of the size is the electron cloud. The nucleus is very small, very dense, very heavy. And it's what takes up the mass of the atom, whereas the electrons hardly have any mass at all, but because of the way that they're scattered around, they take up most of the size of the atom. And also electrons have a -1 charge or a 1- charge. So each electron brings with it a negative charge. Okay. Are there even smaller particles than the electrons, protons, and neutrons? Well, there are. We've found out now that there are quarks. These smaller particles make up the subatomic particles of the neutrons and the protons. Okay, the electrons are not made up of quarks. Only the nucleus is, which is your protons and your neutrons. There are 6 distinctly different quarks that we have discovered, and here is a little image of those. They're called really weird names: up, down, bottom, top, strange, and charm. All right, and there are 3 different quarks in each proton or neutron. Okay, and you can see right here this little diagram. Each proton is composed of 2 ups and 1 down, and the neutron is composed of 1 up and 2 down. And it tells you right here how the charges work out. And you may be wondering, well, where are the top, the bottom, the charm, and the strange quarks? Don't know for sure. Little small, if you catch my joke. All right, moving on here a little bit, talking about atomic models. I mentioned this before. And we use models in science and in life to represent objects or ideas that are difficult to visualize. Sometimes it's easier to show an object rather than to just try to think it up in your head. And models can be a bunch of different things. And specifically referring to the atom, there have been many different models that have been proposed since around 400 BC. That's when humankind first started trying to describe the model, describe the atom, and they used models to kind of try to show and help other people what was going on. The first 2 people that really kind of came up with the model of the atom were Democritus and Aristotle, or I could say Democritus. The interesting thing about these 2 guys is they were diametrically opposed with each other. Both thought they were right or wrong, but unfortunately Aristotle had a much, if you want to call it in the time of social media, he had a lot more followers. And because of that, he was able to just kind of discredit Democritus and put him off to the side. Democritus said atoms make up matter. Everything out there is made up of these atoms. But Aristotle said, no, matter is uniform, right? There's nothing smaller than matter. Matter is just what it is. And there are 4 different elements, according to Aristotle: earth, fire, wind, and water. And those combinations of those make up everything. And because, again, he had more followers, Democritus was kind of dismissed, and of course later on, as we have gone through time, we've realized that Aristotle was wrong, and Democritus is right. John Dalton. Now there is a time span between 400 BC over until like the 1600s. So this is a huge span of time where people basically thought, hey, matter is nothing but combinations of earth, wind, fire, and water. And different combinations, we can make different things. But James Dalton, or John Dalton, excuse me, really didn't agree with that common thought. And he says, no, atoms do exist. And he was the one who proposed the first atomic theory. And this atomic theory stated that atoms are small, indestructible spheres. And he used the models actually shown right here. These are pictures of the Dalton models that he used to show what an atom looked like and how it would join up to make larger structures. And after Dalton kind of got some traction out there, his atomic theory is basically this right here. Matter is composed of extremely small particles called atoms. Atoms are indivisible and indestructible, which means indivisible is you can't break them apart, and indestructible means you can't destroy them. He also said that atoms of a given element are identical in size, mass, and chemical properties. So if you have an iron atom, they're all going to be the same size. They're going to have the same mass, and they'll react the same. They'll have the same properties. So you're not going to end up with a big iron molecule and a small iron molecule, a heavy or light gold molecule. That's not how it works. They're all the same size and shape. Okay, and he also stated that atoms of a specific element are different from those of other elements. He also stated that atoms of a specific element are different from those of another element. They basically, you can't have two identical atoms that are different. If they're identical, they're the same element. You can't combine different ones to have the same element. And they also said different atoms combine in simple whole number ratios to form compounds. The easiest way to explain that is it takes two hydrogen atoms and one oxygen atom, and that combines to make water. And it will always only be water, and it will always and only be two hydrogen and one oxygen. There is a definite pattern to this. This is not chaos. This is not just random things out there meaning all kinds of different things. An item is made specifically of simple whole number ratios to form compounds. Okay? Not half of an atom or part of an atom or anything like that. Okay. And basically in chemical reactions, atoms are separated, combined, and rearranged. Nothing is, again, Dalton thought they were indestructible. We know now that you can split an atom. But we now know, back then he basically said that, look, you can have atoms, but you can't take them apart. And if you take apart an atom, as we know now, we actually split them into different elements. We take a large atom and then break it in half, and then it makes smaller atoms of different elements because we now separated the protons and neutrons. But Dalton's atomic theory said in a chemical reaction, atoms are separated, combined, or rearranged. So if we were to take water, H2O, run electric current through it, we can separate hydrogen and oxygen. And so that would be an example of a reaction. Burning something, putting oxygen into an item with flame, that would also be a different way to combine, separate, or rearrange those atoms. Other chemical models came after Dalton. Thomson was a very famous person. Thomson basically said atoms are spherical with small negatively charged particles, those electrons, and they're evenly spaced inside the positive sphere. This was commonly referred to the plum pudding model. You have a pudding, and inside the pudding are different little nuggets of goodness. Say, for instance, like now you could say mint chocolate chip ice cream, and the negative electrons inside the mint chocolate chip ice cream would be the little chocolate chips. Okay, and that was the Thomson model. And later on, one of the most famous experiments done about models of atomic one of the most famous experiments about atoms was what's called the Cathode Ray Experiment. This is where Thomson basically used a tool to find information out about the model, about the atom. Rutherford came after Thomson, and Rutherford disagreed with Thomson, basically said, no, we have a central nucleus, all right, and it is positively charged, and surrounding that are the electrons. And so this is the model that Rutherford put forward. And this is a very familiar one. It's a very common one that's shown today. We have a positive nucleus, and the negative electrons are on the outside. And he did another famous experiment called the gold foil experiment, where they basically shot and bombarded gold with different heavy particles, and to see what would happen with the charge. And they would run a positive or a negative charge to the side, and it would pull the electrons off and away and cause them to scatter at a different point. The Bohr model came again afterwards, and he said, no. It's similar to the Rutherford model, but except that electrons, they travel in fixed orbits. You don't just randomly zing around. But depending on what orbit they were in, it talked about how much energy they lost or had gained. The more energy you have, the farther out on the ring you are, the more powerful you are. When you lose energy, you drop into rings. And we know Bohr's don't really use his model anymore, except for when we're talking about the position of electrons and when we're using them for bonding. It's very helpful. The most recent model that we have, the current one today, is called the Electron Cloud model. Irwin Schrodinger developed the model. He was a mathematician and basically said the nucleus is protons and neutrons that are in the center of this electron cloud. All right, and Chadwick kind of was the one that really helped show this. And you can see right here, the electron cloud, the reason we use a cloud is because it represents where an electron is most likely to be found. Electrons are moving very, very rapidly at any given moment of time. And so they basically, the darker the color of the cloud, the most likely you are to encounter an electron. And the lighter colors on the outside is where they are not as likely to be found. And here is the nucleus. This is an actual picture of an atom using an electron microscope. And no, the size of an electron cloud is 100,000 times larger in diameter than a nucleus. So people have used an example of like an atom would be the size, say the size of New York City, and the nucleus would be like an atom, an apple in Times Square. That kind of gives you the reference point of how large the electron cloud, how large the atom is comparatively to this small, super dense nucleus. And again, remember the nucleus is where most of the weight is in an atom. All right, and there you go.